Okay, this is video 31.2. We're going to be looking at how induced electric fields and currents relate to energy. Now you might recall that in the last video we learned about Faraday's law, which says the induced EMF is equal to the rate of change of the flux. And we're going to look today at what happens if you have a magnetic field, which for the moment I'll say points into the page. And we have a rectangular loop that we are in the process of pulling out of the field. So we'll say there's a resistance R in that loop, and it has width L, and it's moving with speed V out of the loop. Now because it moves out of the field, the number of the field lines through it is changing. And so the flux is therefore changing. And the EMF is equal to the rate of change of that flux. And the flux is equal to the magnetic field times the area of the part of the loop that is in the field. And that is this area here. And we can call this distance x. So we get the derivative of b times L times x. But notice that b and L are not changing. X is the only thing that's changing. So we get BL times the time derivative of x, which is just the velocity. And so the induced EMF in the loop is BLV. The faster you pull it, the more EMF you get. And now we can also use Lenz's law to figure out the direction of the current that's induced in the loop, because there will be a current in it, and the current will be BLV over R, where R is the resistance of the loop. And to get the direction of that, we start by asking, is the flux increasing or decreasing? And we notice that the flux is decreasing. So we point our fingers, or our thumb, in the direction of the magnetic field into the page. Fingers curl clockwise, and that means the current is also going to be clockwise. And then we can calculate, and the result is that this current here, we now have current carrying wires in magnetic fields, which means they experience forces. And the only side of the loop that doesn't experience a force is the right side here, because it's not in the magnetic field. If we apply the right-hand rule, meaning finger in the direction of the current, or index finger in the direction of the current, other three fingers in the direction of the field, thumb points in the direction of the force, we find that the top of the loop experiences an upward force, the bottom of the loop experiences a downward force, and the left side of the loop experiences a force to the left. The result is that the net force on the loop is to the left. And the magnitude of that net force is ILB, which means that you have to do work. In order to keep the loop moving out of the field, you have to keep pulling it. And that means there's some energy transformations going on, because work always involves changes in energy. So the amount of work you have to do per unit time is power. But remember that instantaneous power is the force times the velocity. And the force, we said, was ILB, but the electric current is BLV over R, which means that the power we have to put in is equal to b squared L squared V squared over R. So that's how much work you're putting into it per unit time, and this is mechanical work. Now, on the other hand, the question is, where is that energy going? You're putting all this energy into the loop. Where is it going? Well, it turns out it comes out as heat in the resistor. And the rate at which heat is produced in a resistor is given by P equals IV, or in this case, or V squared over R. In this case, V is the EMF. This is capital V, the voltage, which is BLV, and that means V squared over R equals B squared L squared V squared over R, and that is the same expression we get for the mechanical work in. So what we've just done is we've created a crude electrical generator. We put mechanical work in, we get electrical energy out. And because it's just a resistive load, that electrical energy is converted to heat, but you could also put a motor there or a light bulb or something like that. And the power out is equal to the power in, assuming there's no inefficiencies involved. So an example of this, problem 26 in your textbook, you've got a loop antenna, which is just a loop, of area A and resistance R. It's perpendicular to a uniform magnetic field, B. So that's area A, resistance R. We have a magnetic field perpendicular to that. It's uniform. The field drops linearly to 0 in a time interval t, which means that the rate of change of the magnetic field is just B over T, or rather negative B over T. And what we want to do is find an expression for the total thermal energy dissipated in the loop. Now remember, the total energy is equal to the power times the time, and the power is equal to the induced EMF squared over R. And so then we ask, well, what's the induced EMF? And it turns out that it's equal to dB dt. And therefore, the EMF is negative B over T. If we square that, we get B squared over T squared R times T. So we get B squared over RT is the total energy dissipated. So relatively straightforward problem. This is the kind of thing that AP really likes. You need to know physics to do it, but it also doesn't take very much time, and you don't need to do a whole lot of math in the process. Now, our last topic for today is something called eddy currents. One of the things that I like to demonstrate, and which I haven't because someone stole the copper pipe I was using for this, is to take a bar magnet and you drop it through a metal tube. Now the bar magnet has a field that looks like this. And as it falls through the tube, each part of the tube behaves like a little loop of wire. So for this loop below the magnet, what happens is that you have an increasing flux, which means that according to Lenz's law, you get a current flowing that way. And that creates its own magnetic field that pushes up on the magnet. You also, in the loop above the wire, have a decreasing flux as it falls, and therefore a current pointing in the opposite direction, which will pull upward on the magnet. The net effect is that the magnet's energy, instead of turning into kinetic energy as it falls, its potential energy gets turned into heat dissipated in the walls of the tube. And it falls very, very slowly. So the magnet's gravitational potential energy turns into heat in the tube instead of kinetic energy, and so the magnet falls very slowly. And these currents that are formed in the metal tube are called eddy currents. And generally you want to avoid eddy currents in engineering applications because they just waste energy. Tomorrow I'm going to check problem 27, which deals with energy in induction. And our next topic is to see how this relates to electric circuits.